The last section of this unit is called solving linear quadratic systems. Um, so the concept is somewhat straightforward, but we're going to see that we rely on a lot of the skills that we've worked on in this current unit regarding quadratics. So as a warm-up, this goes back to maybe the start of grade 10 when you guys did linear systems. In other words, two linear lines. When we talk about solving a linear system, really saying what's the values of x and y that make both of the equations true. So in essence, really that's what we call the point of intersection. We draw two lines. We realize that that's what's special between when two lines intersect. So we might have two lines that intersect like that. What's special there is that only in that one spot where that specific point or that specific pairing of x and y make both equations true. So that's what we talk about solving a linear system. So let's go back and review this. We will not go off and sort of graph this to do this, but we want to do this algebraically. So we want to determine the point of intersections of two functions. In this case, they're both linear functions. One is 2x plus 3, and the one is 5x minus 6. So we could just change this to y equals 2x plus 3. So back into y equals mx plus b form. And then so that's the first equation. And the second equation, second line that we have is y is equal to 5x minus 6. So in order to find that point of intersection algebraically, here we isolate for y. And since we're saying that y is equal to this, in other words, 2x plus 3, and y is also equal to 5x minus 6, we want that common y value, so we can just make them the same. So we have 2x plus 3 is equal to 5x minus 6. So now we're just going to solve this equation. So I'm going to subtract 2x to both sides. So I get 3 is equal to 5 minus 2x is 3x minus 6. Then I'm going to add 6 to both sides. So I'm going to get 3x is equal to 9. And finally, dividing both sides by 3, I'm going to get x is equal to 3. And then finally, how do I get the value of y? I'm going to choose one of my equations. So I'm going to say 1. And then we're going to plug in x into that equation to get the value for y. And so here we're going to get y is equal to 6 plus 3, which is 9. So therefore, the point of intersection is 3, 9. We could actually go off and sort of check our answer with the second equation. So here we have the left side, right side. And the right side is 5x minus 6. The left side is y. So we said that y is 9. And then we plug in 3 for x. And so we get 5 times 3 minus 6, which is 15 minus 6, which is 9. So that combination of x and y, 3, 9, make both of our equations true. Let's just review a little bit on solving a quadratic equation. So here we're going to solve for x. Again, solving for x, meaning finding the value of x that makes that equation true. So in order to solve a quadratic equation, one of the steps that we can do is to get one side equal to 0. The only other way to do it would be completing the square, which looking at this, I'm not going to do. So in this case, we either want to factor or use a quadratic formula. But in order to use either, we need to get 0 to one side, or have one side equal to 0. So in this case, I'm going to add 7x and minus and subtract 14 to both sides. So on the left side, I'm going to get 6x squared plus 7x. And negative 14 minus 6 is going to be a minus 20. Then I'm going to try to attempt to factor this. So let's do product sum integers. So the product is 6 times negative 20, which is negative 120. And then the sum is going to be 7. And I believe two numbers are 120 divided by 8 is 8 and 15. So here we want a difference of 7, so 15 and 8. And since 7 is positive, that means the 8 is going to be negative since 15 is larger. So we want to decompose this. So we get 6x squared plus 15x minus 8x minus 20 is equal to 0. So I want to factor that one pair. I'm going to take out GCF of 3x. And then I'm going to get with 2x plus 5. And then greatest common factor of that one, I'm going to factor out minus 4. And there I'm going to get 2x plus 5. And then come up the greatest there. 2x plus 5, and that's equal to 0. And now I have a common factor of 2x plus 5. So really I'll pull that out. And then I'm left with 3x minus 4. That's equal to 0. So that implies that 2x plus 5 is equal to 0, or 3x minus 4 is equal to 0. So doing the left one, we get 2x is equal to minus 5. Divide both sides by 2, we get x is negative 5 over 2. And then doing the right, we get 3x is equal to 4. Divide both sides by 3, I get x is equal to 4 thirds. So therefore, x is equal to minus 5 over 2, or 4 over 3. Okay, so that's a quick review on solving a quadratic equation, because we are going to have to do that in order to solve a linear quadratic system. So the success criteria for this section is we're going to explore and determine how a linear and a quadratic functions can intersect. We're going to discover that they could be done in 3 ways. Determine how they can intersect by using the discriminant, or really how many points of intersection it's going to have by using the discriminant. And finally, we will solve a linear quadratic system algebraically. In other words, finding the points of intersection or the values of x and y that make both of our equations true. So let's go off and first explore how many ways can a line intersect with a parabola. So I'm going to argue that there's only 3 ways. So in one way, let's say that we have a parabola. That might look something like that. So how can a line intersect? So one way is kind of intuitive. So that might be a line that looks like that. So there could be 2 points of intersection. Another way that it could intersect. So let me draw the parabola. So let's draw the same parabola. And an obvious way, another way to intersect is not at all. So 0 points of intersection. In other words, they never cross. So that's what it might look like. And finally, the last one, I'm guessing you might be able to anticipate or guess what it might be. So here we have a parabola. And the other way it could intersect it would be something like this, where it's just going to touch the parabola. Therefore, it's going to only intersect it in one place. So this line has a special name. It's what we call tangent. So the tangent line touches a curve only exactly one spot or one point of intersection. So here we want to determine the points of intersection, if any, between this parabola, y equals x squared plus 1, and this line. I could tell it's a linear equation, even though it's not in y equals mx plus b form, because the exponent on the x is 1. So the first thing I really want to do is, well, for our first equation, a quadratic is already in y is equal to. In other words, y is isolated. I'm going to do the same thing for the linear equation. So in this case, I'm going to add y to both sides. So I can get y minus 2 is equal to 2x. And then I'm going to add 2 to both sides, so I get y is equal to 2x plus 2. So there's my first equation, might be the parabola. The second equation would be my straight line. So like we did with the two linear systems, really we're saying that y is equal to this, and now y is also equal to this. In other words, now we want a common y. In other words, we're going to state that they're the same, they're equal to one another. So this is the equation that we set up. So we get x squared plus 1 is equal to 2x plus 2. Now we just go off and solve for x. So this is why I did the warm-up that we did. So in this case, I'm going to subtract 2x minus 2 to both sides. So I'm going to get x squared minus 2x minus 1 is equal to 0. Now we try to factor. We hope we can factor, but unfortunately we can't because there's no two numbers that multiply to -1 whose sum is -2. In other words, whose difference in this case is -2, but we know the factors of 1 are only 1 and 1, so there's no way they could subtract to 2. So we have to use the quadratic formula. So my A value here is 1, my B value is -2, and my C value is -1. I'm going to write that out explicitly, so now I don't have to look at my equation in order to solve this. So minus the quadratic formula is x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now I'm just going to plug that in. So b is 2, so minus b is going to be 2 plus or minus the square root, so -2 squared minus 4 times 1 times the -1 all over 2. So this is going to be 2 plus or minus the square root. Well, -2 squared is going to be 4. And -4 times 1 times the -1 is going to be a +4 all over 2. So here this is going to be 2 plus or minus √8 over 2. So this is why we sort of did the lesson on simplifying radicals, because that could be simplified to be 2 plus or minus 2√2. So how did I get 2√2 again? Maybe I'll do this off of the side. √8 is equal to √4 times √2, which is equal to 2√2. So I sort of did that in my head. Sort of all over 2. And now that we can simplify this, because really you could factor out the 2. One way we could see this, we're factoring out the 2, so we're left with 2 times 1 plus or minus √2 all over 2, and the 2's cancels out. So my final answer is 1 plus or minus √2. Now the important thing to note here is that yes, there's two answers there, 1 plus √2 and 1 minus √2. That is not the point of intersection. Okay? In other words, it is not 1 plus √2, 1 minus √2. It is not the answer. Here we actually have 2 points of intersection, and one point of intersection has an x value of 1 plus √2, the other one has an x value of 1 minus √2. So in order to get the actual point of an intersection, we have to do like we did above, is that we need to go off and sort of plug in back into my equation. So in this case, when x is equal to 1 plus √2, I'm going to use my linear equation. I could use the quadratic. That's going to turn out to be a little bit ugly. The easiest one is just using my linear equation. So here y is equal to 2x plus 2. So I'm going to plug in for x 1 plus √2 plus 2. So that's equal to 2 plus 2 √2. So I'm just sort of distributing the 2. And then I got plus 4. And so here I get the final answer of 6 plus 2 √2. So one point is 1 plus √2, because that's my x value, and that will give me a y value of, oh, I made a mistake. Just noticed that because something was looking weird. I'm not sure how that became a 4. I think I was doing some arithmetic in my head in the future, or a future operation, and that 4 stuck in my head. So here this is going to be 4 plus √2. So that's my y value, 4 plus 2 √2. So that is 1 coordinate, or one point of intersection, and then we need to do likewise when x is 1 minus root 2. So we're going to plug that into my equation of y equals 2x plus 2. So here y is equal to 2 times 1 minus root 2 plus 2. I'm going to make that mistake again. So y is equal to 2 minus 2 root 2 plus 2. So in this case, y is going to be 4 minus 2 root 2. So the other point that we have is going to be 1 minus root 2 and then 4 minus 2 root 2. So those are my 2 points of intersection, and they come up really awkward only because we couldn't factor. Therefore, the roots are not an exact integer. So this is why doing things algebraically is a lot better than graphing, because here we're going to get these exact answers. So that was an example, and that's really, in essence, how we solve a linear quadratic system. Really isolating for y for both equations, and then solving a quadratic equation. And then once we have those roots or those x values, plugging it back in to get our 2 points. So another thing we could kind of explore is that sort of like when we're given a quadratic equation, determine how many roots there are by using a discriminant. We could use the same strategy when we're looking at quadratic and linear to see how many points of intersections there are. So in this case, we're given 2 equations. One's a quadratic, y is equal to negative 2x squared plus x minus 3. And the other one is x plus y plus 2 is equal to 0. So what does I want to do? I also want to isolate for y. So thankfully, the quadratic is already done for me. The linear is not so bad. I just need to subtract x and subtract 2 to both sides. So here it's going to be y is equal to minus x minus 2. So here we're going to say that the y values are equal to one another because we want to look for those points of intersection. So here 2x squared plus x minus 3 is equal to minus x minus 2. So here we want to set one side equal to 0. So I need to add x plus 2 to both sides. So we get 2x squared plus 2x, and negative 3 plus 2 is a minus 1 is equal to 0. So from this now, instead of going off and solving it, we just find out what the discriminant is. So in this case, b squared minus 4ac. So let me write this off to the side. A is 2, b is also 2, and c is minus 1. So b squared is 2 squared minus 4. And then a is a 2, and c is a negative 1. So here's going to be 4 plus 8, which is 12. So in this case, the discriminant is greater than 0. So that means there's going to be 2 points of intersection, because there's going to be 2 solutions for x. Another thing that we might be asked is that if we are given a quadratic, so in this case y equals minus 3x squared minus 4x plus 1, we might want to find the equation of a line, of a straight line, so that it's tangent with this quadratic. And in this case, we want this line to have specifically a slope of minus 2. So how do we go off and do a question like that? Well, basically, we need to figure out what the y-intercept is. So we know we're going to have an equation of a line. So let's say the first equation here we're saying is the quadratic, y is equal to 3x squared minus 4x plus 1. Well, the second one, because we don't know what the y-intercept is, well, at least we know the slope. So it's going to be y equals minus 2x. And we'll say the value p is the y-intercept. So we really need to solve for p. So because we're looking for the point of intersection, we're going to make these equations equal to one another. So 3x squared minus 4x plus 1 is equal to negative 2x plus p. So really that's the gist of the lesson. Just isolating for y both those equations and then going off and solving for it. So in this case, we want to put one side equal to 0. So I'm going to add 2x and subtract p to both sides. So I'm going to get 3x squared. Well, negative 4x plus 2x is going to be a minus 2x. And then we're going to have 1 minus p. So in this case, for it to be a tangent, it needs to intersect only in one place. So that means there's only one point of intersection. So that means that this implies that the discriminant, let me do this over here instead. This implies that the discriminant has to be 0 because we only want one point of intersection. So this is going to be kind of weird, because here my a value is 3. We can see that clearly. Oh, I forgot a plus 1 minus p. The b value is minus 2. But the c value here is not 1, but it's actually 1 minus p. Right? So this is my constant because it's not being multiplied to x. So how do we go off and figure out what the discriminant is? It's going to be b squared minus 4ac, which is b squared, which is minus 2 squared, minus 4, times a is 3, and here the c is 1 minus p. But we want this to be 0. We want the discriminant to be 0. So here negative 2 squared is going to be 4, so I'm going to expand and simplify the right side. This is going to be minus 12 times 1 minus p. So 0 is equal to 4 minus 12 plus 12p. So let's simplify the right side even more. 4 minus 12 is a negative 8 plus 12p. So I'm going to add 8 to both sides. So 8 is equal to 12p. So now dividing both sides by 12, we're going to say that p is equal to 8 over 12, but that simplifies to 2/3. So therefore, the y-intercept is 2/3. That's what we just solved for. So therefore, the line, no, it's just asking for the y-intercept. So therefore, the y-intercept of the line is 2/3. That is, y is equal to, let's explicitly write out the equation, minus 2x plus 2 over 3. Okay, so that's an example. The last example that we might have in working with a quadratic linear system is finding a tangent line to the parabola.